Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. A reminder that if you enjoy the show, you can please consider supporting us through Buy Me a Coffee so we can keep making this show you all love. Today I'm joined by Jian Zhang, who will be telling us everything we need to know about VIPER, a fast snapshot isolation checker. Jian is a PhD student at Northeastern University. Jian, welcome to the show.
Thank you, Jack. Thanks for the invitation. I'm really happy to share my research.
Fantastic. So obviously I've given you a very short introduction there, but maybe you could tell the listener a little bit more about yourself and how you became interested in systems and database research.
Okay. I'm currently a second-year PhD student at Northeastern University. My research interests mainly lie in verifying the correctness of computer systems and building efficient distributed systems. My most recent project, like VIPER, focus on verifying the isolation level of databases. Before joining Northeastern, I got my bachelor degree from Nanjing University, China, and a master degree from the Chinese University of Hong Kong. How I became interested in system research? Actually, originally, in my undergraduate, I didn't decide to do system research at that time. I just want to be an expert in computer science. At that time, I didn't decide which area to focus on, like algorithms or systems. But I'm curious. I was always curious about the world, like about the infrastructures in the area of computer science. Especially how they work. I want to figure it out how they were built, how they can work to solve the problems they target, and how to combine the techniques to solve the new problem we encounter. Out of the curiosity, then after my undergraduate, I joined a group at CHK. That group has both algorithm and the system research, so that I can switch across different projects to find out where my interests really lie in. At CHK, I tried some graph neural network research, some distributed graph analytics system research there. And finally, I find personally I was more interested in building systems, especially some elegant and efficient systems. And I find that it would be better if it can have some theoretical guarantees. So that's why I chose my advisor at Northeastern, since we share some similar research interests. As you see, VIPER it's a combination of both theory and system.
Amazing. That's a really good backstory there as how you became interested in that topic. Cool. So today we're going to be talking about snapshot isolation. But before we kind of dig into that a little bit more, can you maybe explain to the listener what concurrency control is and maybe why it's actually important in databases?
Oh, sure. Maybe I should start with transactions. In databases, a transaction is a group of operations that all the operations should be executed or none of the operations should be executed. In SQL, a transaction usually starts with a begin statement and ends with a commit or abort statement. Databases usually manage data that are shared by many users, so that the database should provide concurrent access to the shared data. It should guarantee the users from different places can correct access the shared data. So the database must provide some mechanisms that regulate the interaction between transactions, which means only a few valid transaction interleavings are allowed. It also regulates what values to read from. For example, assume a transaction T1. It consists of two same point queries, like something like select value from table where ID equals to 1. The first query gets the value 1. Then before the second query is executed, there can be another transaction T2 concurrently updates the value to 2. You may not wish the second query in T1 to get the latest value 2, Because if that's the case, the same queries in the single transaction T1 get different values, which may not be expected for some applications above the database. So to summarize, concurrency control is a kind of procedure of managing the execution of transactions while ensuring some properties like atomicity, consistency, isolation, and durability. Atomicity means, as we just mentioned, all the operations are executed together or none has taken effect. Consistency means a transition a database state from one consistent database state to another consistent database state. By consistent, I mean all the invariants hold. For an application, usually it has some invariants. For example, for application of bank transfer, the invariant can be like the total balance of all accounts doesn't change. And isolation regulates what kind of effects of a transaction are visible to another transaction, what kind of interleavings or schedulings of operations are allowed. Durability, I mean, once the transaction has committed, its effects will never disappear, will always remain in the database. So without concurrency control, the atomicity, consistency, isolation, durability cannot be ensured. For example, if a race condition occurs, some invariants may be broken and consistency may be violated.
Awesome, yeah. So that just emphasizes how important transactions are and how important concurrency control is in a database. So you touched on there that one of the 4 components of the ACID acronym there, isolation. And can you maybe tell us why? Because obviously a lot of your work here has been about checking and verifying isolation levels of a database. Can you elaborate on why we need to check these and maybe talk a little bit more about the different levels?
Okay, sure. Maybe we can imagine a scenario. Consider a company. It has developed several web applications running within the trusted domain of their own company. While the data of applications are remotely stored on some cloud databases in untrusted domain. So there is a contract between the web applications and the cloud databases. The contract is like what kind of guarantee the database should provide. Isolation levels are a kind of contracts. For example, the contract can be the execution of transactions must comply with some specific isolation levels, serializability or snapshot isolation. Maybe I should explain what serializability is. Serializability is the strictest isolation level in the transactional theory. If we say execution of transactions is serializable, we mean this execution is equivalent to another serial scheduling of transactions, which means it's equivalent to it appears to execute the transactions one by one. Then those web applications developers, namely those database clients, may want to know whether the database they are using indeed provide correct isolation level. Since isolation level or concurrency control are really important to them, they built their application based on the isolation level, and even a minor violation of isolation can lead to severe consequences or financial losses. By far, clients can never know the exact answer. They can only use some unit testing to test, but testing is never sound. They have to assume the answer to the question whether they provide correct isolation level. They have to assume the answer is yes. Testing is never guaranteed to cover all the anomalies in the execution. This is one motivation of R. And the second scenario is that database developers they keep adding new features to the current version of databases. So in the iteration of database developers keep adding new features and improving the performance. Before release the new version, they may want to test test the current version of database to guarantee the correctness. So it may be useful for database developers to be able to check the isolation level before they release the new version. And actually, from our based on our knowledge, I think these concerns are reasonable, since it's really hard to implement isolation level efficiently and correctly. So it's reasonable for clients to not to trust the database completely and have that kind of concern. For example, for some databases, I don't mention their name here, so some databases they were ever found to violate SI for 3 times, starting from the very initial version V0 to the version 20. And some other databases, it supported snapshot isolation and serializability in the very beginning. But later, they admitted their snapshot isolation implementation was buggy and just gave up that. Now, serializability is the only isolation level it supports.
Wow, it's quite surprising. Cool. So plenty of good reasons there as to why it's important to check the isolation level of a database. So you mentioned it again there. So like snapshot isolation, maybe you can tell the listener how it differs from serializability and what potential anomalies can happen under snapshot isolation.
Okay. Recall that serializability is the strictest isolation level. Snapshot isolation is a weaker isolation level than serializability. Intuitively, but not very precisely, snapshot isolation can be regarded as in the beginning of the execution of each transaction. The transaction tries to capture a snapshot of the current database state and then executes operations based on that snapshot. Finally, after the transaction executes all the operations and it tries to commit, before it commits, it needs to detect conflicts. If without conflicts, the snapshot can be merged back into the current database state. Otherwise, it should abort. And for example, assume we have a simple table. It consisting of only 2 rows, X and Y, and with values 1 and 2 respectively. When transaction T1 starts, it captures a snapshot of the database state, X equals 1, Y equals 2. And then T1 updates X to 3. Before it commits, another transaction T2 also starts, captures the same snapshot. Since T1 hasn't committed, so T2 captures the same snapshot and updates Y to 7. Each transaction has an illusion like it's the early process running in the database without being affected by each other. After T2 made the modification, next T1 tries to commit and detect conflicts. Since there is no other transactions in its life cycle, namely after its capture of snapshot and before its commit, there is no other transaction writing the same key X, so there is no conflict. So it's a snapshot X equals to 3 and Y equals to 2 is merged back into the initial database state. So X is updated successfully. Similarly, T2 tries to commit and finds that the concurrent transaction T1 didn't update Y, so there is no conflict in writes. So it also commits successfully, and Y is written back to the database state. Finally, both transactions commit, and the 2 snapshots are merged to get a new current database state, X equals to 3 and Y equals to 7. This kind of scheduling is not allowed in serializability. In serializability, you cannot modify the database concurrently. To be formal, write skew is the only kind of anomaly that is allowed in SI but not allowed in serializability. Earlier gave a formal definition, graph definition of SI. It defines a start ordered serialization graph, or we call SSG for short. RDA use one node for each transaction, one node to represent each transaction, and one edge to represent a dependency between two transactions. Actually, RDA defined 4 types of different dependencies: read dependency, write dependency, start dependency, and anti-dependency. Here, for simplicity, we will just combine these 4 types of dependency into 2 types of dependency, anti-dependency and non-anti-dependency. RDA defined SI as all the cycles in this graph, SSG, should have at least 2 adjacent anti-dependency edges, or we call CAD for short. If a cycle has at least 2 consecutive anti-dependency edges, we say this is a CAD cycle and is allowed by SI.
Cool. Okay, so just to recap that, we have this formalization of isolation levels from ADIA, graph-based, and that you can characterize the occurrence of a right skew anomaly or an anomaly under snapshot isolation by the fact that it has 2 adjacent anti-dependency edges emanating from or into a node, right? Cool. That's great stuff. So there's obviously been some work previously on verifying isolation levels in databases, and it's looked at maybe serializability more than snapshot isolation. But what are the challenges that come with trying to verify and check for snapshot isolation versus serializability? What are the additional challenges?
Okay, good question. Actually, both verifying serializability and snapshot isolation have been proven to be NP-complete problems. So both of these, the problems are computational challenging. But the additional challenging of checking SI is that serializability is widely agreed. Almost everybody knows the definition of serializability. They agree on the same definition. But for snapshot isolation, different people have different understandings. There are multiple SI variants, like earlier SI, in the paper, A Critique of ANSI Isolation Levels, there is the original definition of SI and strong session SI, general SI. There are many different SI variants. So how to propose a unified approach that can be applied to different SI variants is one of our main challenges. Since serializability, naturally from the definition is like whether you can find a serial execution of transactions, right? That's equivalent to the concurrent scheduling. So it's more natural that you model the history with the graph, where each node is a transaction and each edge is a dependency. If you can find the topological sort of the graph, then you have already found the serial execution that's equivalent to the original concurrent scheduling. But for SI, by far, we don't know. We don't know whether we can model it as a graph where the acyclicity, each topological sort corresponds to one valid scheduling. We don't know that.
Great stuff. With all the challenges in mind, then that come with checking snapshot isolation, tell me how VIPER works, and specifically, I'd like to know more about this concept of a BC polygraph.
Okay. This is gonna be a long story.
Okay, I'll strap myself in. Go for it.
Okay. Firstly, maybe I should start with the architecture of VIPER. I just briefly introduce the architecture. VIPER has 2 main components. One is history collector, and the other is the checker. Okay, the history collector, if without originally clients keep ensuring transactions to databases and receive responses from database. The history collector is a library that logs these transactions and the returned responses. When we use VIPER, we put the history collector in between the clients and the database. The history collectors work as a shim layer between the clients and the database and are transparent to applications because they provide the same key value semantics. After running the history collector for a while, we can get a series of transactions and their execution results, which is called a history. Then VIPER passes the history to a checker. The checker is responsible for answering this question: is the history snapshot isolation? Okay, next we switch to the concept of busy graph first. Busy graph targets the white box setting, while busy polygraphs targets the black box setting. Actually, with RDS formulation of SI, there is already a straightforward approach to checking SI. You just need to search for all the cycles in SSG and check the properties, CAD properties for each cycle. You just find all the cycle, and for each cycle you check whether the cycle has at least 2 adjacent anti-dependency edges. However, since this approach's runtime relies on the input SSG, so if the SSG is very dense, which means given a fixed number of nodes, there can be a large number of edges, and potentially there can be a large number of cycles. So it's not very efficient to enumerate all the cycles and check the CAD properties for each cycle. So our thought is, can we check SI without enumerating all the cycles and without checking the CAD properties? Our idea is to design a new graph data structure called busy graph, which has a one-to-one correspondence to original SSG. Crucially, a busy graph has cycles if and only if there are non-CAD cycles in the corresponding SSG, which means the non-CAD cycles, which will be rejected in SSG, remain in the busy graph, while the other cycles disappear in the busy graph. Then we only need to check the acyclicity without caring about the cycle types. Now we introduce how to construct a busy graph given a SSG. You can imagine a SSG on the left part for any transaction Ti, just for any node in the SSG. It's split into 2 nodes, Bi and Ci, representing the begin and commit of transaction Ti respectively. Then we add an internal edge from Bi to Ci to enforce the requirement that the begin commit should happen before the commit for each transaction. For any non-anti-dependency edge from Ti to Tj in the left SSG, we add an edge from Ci to Bj from the commit of Ti to the begin of Tj in the busy graph, indicating that a transaction like Tj is only allowed to observe those transactions that logically happened previously. For any anti-dependency edge from Ti to Tj, we add an edge from Bi to Cj, which is the reverse direction from non-anti-dependency edge. So this is to require that the beginning of Ti happens before the commit of Tj, so that Ti didn't see the write by Tj. After that, we get a complete busy graph. In the original SSG, the edges have types, but in the busy graph, the edges don't have types. All the edges are equivalent. By far, we have illustrated how to construct a busy graph. Then, if the busy graph is acyclic, it's SI. If otherwise, it's not SI. But by far, we assume that all the dependencies are already available. Then we can build a busy graph. However, this assumption may not always hold, since clients may use black box databases like cloud database. Then clients have no access to the internal scheduling of transactions. The only available information is what transactions they issue to the database and what kind of responses they get from the database. Then how to check SI. For example, imagine two transactions, T1 and T2. T1 updates X to 1 and T2 updates X to 2. But they are concurrent. We don't know which one happens first. So the dependencies between them are unclear. It can be there is a write dependency from T1 to T2. It can be there is a write dependency from T2 to T1. So how to check SI without some of the dependencies? A naive approach is to try all the possible schedule of writes and build a busy graph for each possibility. For example, here we can assume the dependencies between T1 and T2. For one, if T2 overrides T1, we can build a busy graph. For the other, if T1 overrides T2, we can build another busy graph. Then we can answer the question whether there exists a busy graph that is acyclic. If yes, we have already found a valid schedule and the history is ASI. Otherwise, there is no valid schedule and the history isn't ASI. However, due to a factorial number of right order, the number of derived busy graphs can also be huge and hard to check in a reasonable time. A simple idea is to use another graph data structure called busy polygraph to model all the possible busy graphs in a single data structure. One way to consider busy polygraph is that it's a superposition of many valid busy graphs that share the same history. I will briefly introduce how to construct a busy polygraph. First, busy polygraph shares the same vertex set with busy graph. And second, for those edges that exist in all the busy graphs, they are still included in the busy polygraph. But what about those edges that only exist in some of the busy graphs? Like an edge only exists in, recall that we have two busy graphs for the example T1, for the concurrent T1 and T2. So maybe one edge only exists in one possible busy graph and doesn't exist in another busy graph. Recall that each busy graph corresponds to one possible schedule of writes. Different write orders are not compatible with each other, so that the edges from different busy graphs cannot coexist in the busy polygraph.
So if I'm just gonna repeat this back to you, I clarify my own understanding. So from an SSG, we essentially if we assume that an SSG has all the information of a given execution, that a BC graph is essentially like a compressed version of an SSG, right? Is that the correct way to think about it? In the sense that you are removing some edges, you're removing the type from edges, and you're like certain edges have been removed from the graph, essentially the ones that you don't necessarily care about exactly. And then a polygraph on top of that factors in the fact that in a black box database scenario, we don't actually have control over the internal mechanism, so that in this case, we have to kind of we have to account for the possible different states that could have happened within the database. Is that the right way of thinking about it?
I think your answer is mostly correct, actually.
Okay, cool. Great stuff. So VIPER also has another optimization in it you use called heuristic pruning. Can you maybe explain or give the listener like an intuition to what this is and how it maybe works?
Okay, this is a very simple optimization, since we observe that even we know that snapshot isolation allows the transaction to fetch a really old snapshot, to read from a really old snapshot. But that's not a common practice in production databases. This is our observation. A snapshot isolation database implementation rarely delays the write for a long time. So our idea is to heuristically assign orders to those transactions that are far from each other, because databases are less likely to reorder them. So by adding those heuristic edges, VIPER can prune some constraints that violate those edges, hence can reduce the number of constraints decisions to make and accelerate the SI checking. For example, if we have two concurrent transactions, we don't know which one happens first, which means there is a constraint from C1 to B2 or from C2 to B1. A constraint is similar to the semantics of exclusive OR. If we add a heuristic edge from C1 to B2, then the constraint is reduced to a known edge without any uncertainties. After adding heuristic edges, if it returns accept, then it's already done because we have already found a valid schedule. Otherwise, if it returns reject, it doesn't mean indeed a rejection. The recycle may be introduced by the heuristic edges we added. So we need to relax the definition of far and repeat the procedure. Specifically, we use the constant k to measure how far two transactions are from each other and double the measure k each time. Finally, when k equals to n minus 1, where n is the number of transactions, if the still rejects, then VIPER rejects the history. The history is not SI. So this kind of optimization only accelerates the positive histories, which means those snapshot isolation histories. But if the histories that are not snapshot isolation, this kind of optimization may bring some negative effects.
Cool. So with all this in mind, and let's talk about the results, and can you tell me about the experiments you ran? I mean, how do you even go about evaluating a tool like VIPER? And then, yeah, let's start off with that. Then we can talk some numbers afterwards. Yeah, tell me about the experiments you ran first.
Okay. Our evaluation plan mainly answers 3 questions. The first question is, what's the VIPER's performance? How do these compare to existing checkers and natural baseline? The second question is, how do VIPER's components contribute on the different workloads and different setups? The third question, can VIPER detect non-real-world SI violations? For question 1, to compare with natural baselines that we built, we evaluated VIPER on 5 benchmarks, which is a combination of macro and macro benchmark. Some of the benchmarks are some random transactions that consist of read-only transaction and write-only transaction, and some benchmarks also have range query operations, and some other benchmarks are simulations of real-world workload, like C Rubis. Rubis is a bidding system like eBay, and the C Twitter is a simulation of a tiny Twitter. We use a configuration of 1,000 users. And to generate histories, we run our benchmarks on 3 databases, TIDB, SQL Server, and YugaBDB. All the databases are configured to run on the SI. We use 24 concurrent clients for all experiments, and we just record the total runtime for the performance comparison. And to compare with another existing SI checker, AO, if we run the workload of blind writes, AO can run fast, but can miss some data anomalies. So it's not solving the exactly same problem as VIPER. So to make the comparison fair, we need to let AO run in the sound mode, just as VIPER. So we configure both VIPER and AO to run the append benchmark from Jepsen, which is a distributed database testing tool. In the append benchmark, clients issue atomic append operations to some keyed lists. And by reading the lists, each list is a list of integers, so it contains all the appended values. Clients know the right orders of appends. Given the version order of all the writes, AO is also sound. So we compare with VIPER with AO in this mode. For the second question, how do VIPER's components contribute? We run VIPER on 5 benchmarks with 5,000 transactions and measure the wall clock running time and break the runtime into different phases like parsing, graph construction, encoding, and solving. For the third question, we downloaded can VIPER detect non-real-world SI violations? We download real-world public SI violations reports and test whether VIPER can reject them. And also, we manually inject 3 types of anomalies into histories to see how VIPER performs on different types of anomalies.
Cool. So I guess what's the headline here? So how much faster is VIPER over the state of the art?
Firstly, the performance comparison mainly consists of, we have 2 figures about that. Firstly, we compare VIPER with natural baselines that we built. Why we built natural baselines? Since the other checkers there are usually not sound, so we built some natural baselines but the core SMT encodings of baselines are borrowed from existing work, and we implement them by ourselves. All checkers are run on blind W histories, this benchmark of various sizes. Our evaluation results shows that VIPER can outperform all the baselines consistently and can handle a 15 times larger history. And this is the comparison with natural baselines. We also compared VIPER with AO in the sound mode of AO. Our evaluation result shows that both VIPER and AO can the runtime scale linearly for checking the append benchmark, which means there is no fundamental performance gap. This is because the right order has been revealed, so the checking SI is linear for both checkers. In particular, by having right order, the BC polygraph have no constraints. The difference in that figure, different slopes of the lines are just due to the difference of technical stacks. VIPER is implemented in Python, while I use Clojure language, which is a JVM-based language.
So my next question is this is VIPER's an amazing tool. How do you think software developers, database administrators can leverage the findings in your research? My question here is more, what impact do you think your work can have, or maybe already has?
As we mentioned before, the first application scenario is if your database supports SI. As a database developer, engineer, you can integrate into your existing testing pipeline to test the correctness. Actually, I know some production database, they have such testing pipeline, but such like Jepson-like testing pipeline. But I think our checker can be integrated into that kind of testing pipeline to help improve the reliability. And while we develop such method, I think our method has some advantages over existing method. Like other method, existing method like formal verification, as we know, the cost is too high, and testing tool is the common approach we use to test the correctness. But test is not sound, so that's why we developed this method. It has an acceptable runtime cost, and you don't need to make any modification across different system versions, different database versions. Its implementation is independent, and it has a higher runtime cost than testing, but it can actually downgrade to testing if the time is limited. You just need to exclude all the constraints and only consider the known edges, just like Jepson does.
Nice, cool. I think it's really impactful work, and I know that it, like you say, it's good to know that. I mean, I guess on this, sorry, just for a quick side, are you aware of any commercial systems that are thinking of integrating VIPER into their current workflow at the moment? I see that one of your co-authors works at Cockroach, so I'm thinking maybe Cockroach DB might be using it internally.
Yeah, actually, my an employee from Cockroach DB, they contacted us before to seek for potential opportunities for collaboration.
Yeah.
They have such testing pipeline in their company. I heard of that.
Cool. Great stuff. I guess whilst you were working on VIPER then, Jian, like, what was maybe the most interesting thing that you learned whilst being on this project?
The most unexpected part for VIPER is perhaps the new characterization of SI, snapshot isolation. In the very beginning, we didn't expect it to be as simple as a cyclicity of a graph. I think this is the kind of bonus. This is the most interesting part. Before, only serializability can be characterized as a dependency graph has no cycles, so that you can find a serial scheduling of transactions that's equivalent to the concurrent scheduling. It's very easy to understand the serializability. In the past, if you ask somebody what SI is, it can be really hard for them to tell what SI is, since they may forgot about the read, write, and commit rules of SI if he's not working on the database implementation. However, if you ask them what serializability is, it's highly possible for them to tell something, like equivalent to a serial execution. But so I think Bernard sees that it is just from the perspective of clients, SI has a great parallel to serializability. This is what we learned. And I think this is the most interesting part I have learned.
Yeah, fascinating. I agree. That's a really interesting finding, for sure. Cool. So it's time for the last question now, Jian. The last word. So, what's the one thing you want the listener to take away from this podcast today and from your work with VIPER and verifying isolation levels?
Okay. I think we developed a new graph data structure to characterize SI, which can help people to understand snapshot isolation from the perspective of clients. And based on that, we developed VIPER, which is a fast, sound, and complete SI checker.
Well, yeah, that's a wrap then. So thank you so much, Jian, for coming on the show and talking to us about VIPER today. If the listeners interested to learn more about VIPER and all of Jian's really cool work, we'll put links to everything in the show notes. You can go and find that. And another reminder again that if you enjoy the show, please consider supporting us through buying me a coffee. And yeah, we'll see you next time for some more awesome computer science research.